Okay, parent function y equals absolute value of x. We're not learning parent functions today. Like we're going to assume you know the parent functions. What we're going to learn today, maybe we should title it this, is transformations. Why the groaning? Geometry transformations?
I hated it.
Well, this is different than that, so give this a chance. This is algebra transformations using equations to move things around. So yeah, in geometry, you did have translations and dilations. We don't really call them dilations here, but we do have transformations where we move things around and stretch things. I think it's easier than the geometry version, but I guess you can be the judge of that in a moment. So we're going to do all of these with absolute value, but the good news about transformations is once you understand the rule, or rules, plural, work for all of the parent functions. So I kind of even debated on, it doesn't matter which one we start with, because when we start doing these rules, they work the same way. So I picked absolute value because we're going to do more work with that on Friday. And so I thought, well, let's work with that one. That way we will be more familiar with it. The other option was a parabola because you're most familiar with a parabola, probably. But we'll do absolute value. Let's start with the table of values. And this is way too many. We don't need that many. Let's just go -2 to 2. That's plenty, especially given the fact that we know the basic shape of an absolute value. So let's see. Absolute value of -2 is 2. Absolute value of -1 is 1. And the rest are even easier than that. It just makes the negatives positive. So let's plot those points. So we'll have a, previously we knew the absolute value was a v at the origin. Now we're going to have a little bit more detail on that. So -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. And it would keep going forever in both directions. So if you just draw your line and you just keep hitting the next corner, you end up with a fairly straight absolute value. That's the parent function. No transformations have happened yet. Just as a recap, we could ask some of these other questions, like domain, and range, and x-intercepts, and y-intercepts. You guys know what asymptotes are?
Nope.
We'll skip that one then, and we'll jump to symmetry, even though we hadn't talked about symmetry either. I'll put Brenna on the spot for that one. Logan, how about the domain for the absolute value function?
Is it negative infinity, infinity?
Yes, it is. Nicole, how about the range?
Is it bracket 0 and 30?
Yes, it is. Megan, how about x-intercepts?
Isn't it just 0?
It is. Can you give it as a point?
0, 0.
0, 0. And Allie, the y-intercept? Also 0, 0. Kind of boring. Asymptotes are when a graph gets closer and closer to a line but doesn't hit it. So we may not have used the term, but we saw some of those in our parent functions. Some of those had asymptotes. Exponential and logarithmic both have asymptotes. But this does not have an asymptote, so none on the asymptotes. Brenna, not looking for anything technical here, but does that graph have symmetry? Yes, and what would you say it's symmetric across? Hold on, let's see if Brenna can get it, then we'll okay. So how did you know it had symmetry?
Because it's even on both sides.
Okay, and so across what could you fold it and make it match?
The y-axis.
There you go. So it's symmetric with the y-axis. So we can say y-axis symmetry. Okay, that's not really the point of today's lesson, but that's some good review stuff thrown in there. All right, the point of today's lesson is the translations, what we can do with this thing. Probably the easiest one is to tack on a +3 at the end, or a +7, or a +5, or a -3. Any idea what that does to the graph?
Where it is at 0 on the parent function, it goes up the y-axis.
So where it is at,
That's where it is.
that would go up 3. Is that what you're saying? Yes. What about all the other points?
It would also.
It would also go up 3. So it would move everything up 3. And so once you know how to do translations, you don't go back and do another table of values. You just know what the parent function looks like. And exactly what Cody said is, well, let's just move all those points up 3. And he started with the best one to start at. And that would be the vertex, usually at 0, 0, has now been moved up 3. And then from there, we can just do the v. So over 1, up 1. All the way out. Again, the point of using translations is you don't have to plot points anymore. You know what the parent function is. You know that the +3 moved it up 3. And so just shift the whole thing up 3. So let's not graph this one, but what if we had absolute value of x minus 5? What would that do to the graph? Down 5. Oh, maybe parentheses or something, because we're not going to graph that one. All right, now let's get a little bit more confusing here. Let's put x minus 2 within the absolute value bars. So you know that at the end it shifts it up or down, but if it's in there with x, do you know what it does to the graph? Okay, so it shifts it left and right. Let's start with that. If it's in there with x, it does an x thing. That's the easiest way to remember it. If it's not in there with x, it does a y thing. So this one's up and down, this one's left or right. Now, do you know which way it goes? It goes to the right too, which might feel backwards because x minus 2 feels like, well, minus 2 is that way, but the x stuff is always backwards. This is going to be right too. You just need to convince yourself of that. Plug in x equals 2, and what do you get if you plug in 2 for x? If I plug in 2 for x, 0. So 2, 0, my graph has been shifted to the right by 2 spots. And again, I'm not plotting any more points, or I'm not doing a table of values. I will plot some points, but not from a table, just from moved it to the right 2, and from there I know what an absolute value looks like. It's the same shape as all the others, it's just been shifted to the right. What about if we had x plus 7? That'd be maybe a pain to graph, but we're not graphing it. So if we had y equals the absolute value of x plus 7, how would that change the parent function? 7 to the left. Our non-graphed example. All right, C says dilation. What does dilation mean? It's bigger or smaller, yeah. We're stretching it out some way or another. So, say dilation slash stretch. Y equals 2 times the absolute value of x. So do you know what that's going to do to the graph? I mean, you know it stretches it, but like, which way?
So make it y or y. Yeah.
Okay.
Y.
it doesn't make it wider. I would say it ends up making it narrower, but it makes it narrower because it's stretching it out. It stretches out the y points. It's not in there with x, so it's doing something in y, and it's going to stretch it out this way. For absolute value specifically, that sort of looks like a slope, right? Think about y equals mx plus b. That's sort of playing the m role, and so it'll have a slope of 2 on either side. So it didn't go anywhere. The origin didn't go anywhere. The vertex didn't go anywhere. But then instead of going over 1, up 1 on either side, we'll go over 1, up 2, because we've stretched it out. So we'll stretch our y values by 2. Again, it's sort of like slope for absolute value. For the others, they're not lines, so it's not slope, but it does that same thing of stretching out the y values. Especially if you have the others in view, you can tell that that's a steeper graph. It is narrower. I'm going to avoid using that word because narrower suggests you've changed something in x. But what you've really changed is something in y, so you've stretched it out. The effect is making it narrower, but I don't want to say that. The cause is a stretch. The effect is it looks narrower. What if we had 1/4 times the absolute value of x? What would that do? Yeah, it's like squish it. That's a fancy math term for you. Squish by 1/4. Like your slope would be 1/4. And I'm not going to draw it exactly, but we could kind of roughly draw out a 1/4 slope graph. It would be squished. Yes, sir. Yeah. All right, for this last blink, we're going to try to throw everything in together. And I'm going to add one more thing because I'm sort of out of spots here. So let's do negative, that's the new thing, 3, absolute value, x plus 2, minus 1. All right, well, let's take these things one at a time before we start trying to graph it. What does the minus sign do? Good. It flips it, and it flips it up and down. Because it's out front, it's a y thing, so it flips it up and down. If it was in there, if the negative was on the x, it would switch it, flip it in the x direction. We don't do very many of those because those get complicated. But a negative out front is easy to handle. We'll flip it over. Okay, so there's what the negative does. Let's see how many colors I can come up with. Let's see. I'm going to pick on some people here. Ellen, how about the 3? What do you think the 3 does? Good. So that stretches it. That's sort of the new slope, if you will. It's going to stretch it out. Alex, how about that plus 2? What's the plus 2 do? Good. So that plus 2 will be left 2. And then lastly, got here, Aaliyah, how about the minus 1? Okay. What will it just, can you just tell me what it's going to do to the graph, which way it's going to move it? Down 1. Okay. And the order you do these is kind of tricky. It doesn't really matter. But it feels like to me the best order is to work from the back forward, so like work them in reverse, or use them in reverse. So I'm going to go down 1, left 2. That'll be my new starting point. So there's down 1, left 2. And now I have to stretch it and flip it. I kind of need to do those at the same time, right? Because if I only stretch it, it ends up pointing up. But I need to flip it. So it needs to be flipped and stretched. So I'm going to go down 3 over 1. Down 3 over 1. In some sense, that's as hard as we can make it, because like that had all of the changes we could do. We did. We flipped it, we stretched it, we moved it left and right, we moved it up and down. All right, this next page is kind of a summary of what we just said. I think this goes quick. Maybe not. We should pick on people to make sure. Reese, if there's a +4 at the end, what's that do to the graph? Any graph. It doesn't matter which graph you're talking about. What's that +4 going to do? Good. That's all we're looking for, is that +4 makes us go up 4. These are sort of in pairs, by the way, so if you get the second, if you're the second popsicle stick in the pair, I think you kind of have it easier. Caroline, so what's -4 at the end do? It's down 4. Pick on multiple people at once here. In fact, why don't you see if you can finish the rest of the page? Although 7 and 8, never mind. We may need to talk about 7 and 8. Luciana, what about number 3? What does that x plus 3 in parentheses do? Good, left 3. The x stuff is backwards. Kennedy, how about x minus 3 in parentheses? Good, right. Cooper at 2 out front. Okay. I'm going to tweak that by a little bit. I'm going to say vertical stretch by 2. Vertical meaning up and down. Right? I'm going to stretch it out this way. Dantre, how do you want to explain what number 6 does? You said the right thing, but you did the wrong thing with your hands. You said vertically squish, but that's not this. It's this. It's a vertical squish, so that was kind of weird. You said it exactly right. Vertical squish by a half. Right? It's like you're going to squish it down. It might have the effect of making it look wider, but we don't want to say it makes it wider. We want to use vertical language, so we want to say a squish by a half. Okay, we hadn't done 7 and 8. That's a little bit trickier. Any guesses what? I'm not going to pick on someone because we hadn't done this, but a 2x on the inside. So it does something horizontally because it's on the x. And which way does it go? Like, does it stretch it out or does it squish it in?
Squishes it in. Sure.
Oh, I think I heard both. I'll remind you that the x stuff appears to be backwards. +3 is left 3. X minus 3 is right 3. So at 2x, I think you were right the first time, it actually squishes it. It's a horizontal squish. The right word, I guess, would be compression, would be the fancier word, but squish is just as well. And a 1/2, again, this feels weird. It doesn't feel weird that it's horizontal, right? It's in the x, so it makes sense that it's horizontal. But instead of squishing it horizontal, it actually stretches it horizontal. X stuff is always just, it feels backwards. All right. I definitely can call on someone for number 9, but we're out of popsicle sticks. So we're also almost done. Actually, let's flip them back over. So everybody's back in the draw side. Everybody's back on the hot seat for a super easy question. Hopefully easy question. Cole, how about that negative out front? What's that do? Flips it. Which way does it flip it? This way or this way? What'd you do there? Yes. So we'll say that is a vertical flip. Vertical reflection would be the fancy way to say that, but flip is what most people think when they see that. It flips it over. What do you think the negative on the inside does? It flips it horizontally. Horizontal flip. Okay. We need a little more practice on this stuff. So, yes. Yeah. So what we're going to do is Kahoot, and then we'll work some of the homework together, and then I'll let you on your own to work and check in time. Oh, we got tons of time, so we're good. So, grab a phone. We're going to Kahoot one more time.